Hey, Chemsters, this is Mrs. Vandalay bringing you the last section of video notes. Woohoo! All right, something to celebrate. So we are going to be talking about the last set of functional groups. Notice that we've been pairing them up, and I call them, they're like close cousins. So we had like aldehydes and ketones. They were only off by a carbon, weren't they? We had carboxylic acids and esters, right? They're off by a carbon. We had alcohols and ethers. They're off by a carbon, right? You take off the H, you put in a carbon, and there's the cousin. So we're going to do the same thing with amines and amides. They are what I call cousins of each other. They're only going to differ really by that, this time, not a carbon group, a double bonded oxygen group, okay? So we will start with amides. Section 10.20 are amides, and they are derivatives of carboxylic acids. Now, keep this in mind. Here's my carboxylic acid. What's going to happen is that we're going to drop the OH and put in a nitrogen group. So do you remember what this is called? That's ammonia. Do you remember what this is called? Ammonium. So this AM, if you will, implies the nitrogen groups. So what we're going to do, we're going to take off this OH and we're going to put in a nitrogen group. So we're going to take off the oic acid ending and we're going to end with amide. So if I were to look at this, this would have been methanoic acid. Well, take off your oic acid and put in amide. So it becomes methanamide. How many carbons are here? 2 carbons. So instead of being ethanoic acid, it will become ethanamide. The O should be on, well, actually the double bond should be over by the carbon instead. So we have 1, 2, 3, 4. Instead of being butanoic acid or butanol, all right, we have what? Butanamide. And the last one is, you might remember this as being benzoic acid, so this becomes benzanamide. Okay, so let's look at problem number 1. Let's name this. Okay, look how this is arranged. Okay, this is not implying a carbon single bonded with an oxygen, single bonded with a nitrogen. If you see it like that, all right, it's not going to work that way. You're going to find out if you try that, carbon won't have enough bonds. Carbon always gets 4 bonds. Carbon doesn't really exist well with lone pairs, okay? So you end up with a double bonded. So go ahead and see what you can do naming that one. I'll give you a few seconds. All right, welcome back. So I have 1, 2, 3 carbons, so it becomes a propanamide, but you have another group here, and that is your 2-methyl group. Okay, so it's a 2-methyl because it's on carbon 1, carbon 2, 2-methyl propanamide. All right, what about the next one? Draw a structure of 1-methyl cyclobutane carboxamide. All right, that is a mouthful, isn't it? All right, but see what you can do with this. All right, let's see what happened. Well, here is my cyclobutane. All right, remember we had a carboxylic acid, so this would be a cyclobutane carboxylic acid. So this would be a cyclobutane carboxamide. All right, and don't forget you also have a 1-methyl. Well, this had to be your first carbon, so here's your 1-methyl cyclobutane carboxamide. Okay, now these are all examples of what we call primary amides. All right, and what does that mean? Well, you're going to look at your nitrogen this time. Okay, your nitrogen has 2 hydrogens with it, and that makes it primary. So instead of looking at your number of carbons attached to a carbon, let's say primary alcohols and things like that, we are looking at the nitrogen. So if you have 2 hydrogens on this nitrogen right here, it's a primary because we can be substituting. We can take off the hydrogen and put in some carbons, can't we? Yes, we can. So this would be an example. Notice I have 1 carbon. Well, actually, in addition to this one, I have a total of 2 carbons attached to my nitrogen, so it is secondary. And take a wild stab. All right, here this nitrogen has 3 carbon groups. They can be the same or they can be different, and so that makes it a tertiary. And what happens is we're going to find out when we go into the amines and we name it like that. The naming gets a little more complicated. It really does. So we'll hold off and show you that with the amines. Okay. So real quick, urea is what's called a diamide. All right. So 2 amide groups of carboxylic acid. So urea is the natural end product of protein metabolism. By the way, this would be your dicarboxylic acid or dioic acid. This is urea. Now, a couple things. This entire semester started off with how one chemist proved the top dog of chemist Berzelius wrong. Remember back at the very, very beginning, Berzelius said, oh, these compounds are God-made. We cannot change. We cannot make anything that God has made. I don't know if you call it that discussion. And then Wohler was his student. And later after that, he came around and he realized he made urea. He made urea out of salts. Okay, that was kind of nuts. And he wrote back to Berzelius and he said, hey, I think I made this urea. And remember, Wohler started out as a med student, so he was familiar with this urea. He knows what he made. So this is the compound that really began organic chemistry. So you can either thank it or curse it. I don't care which, all right, but it is what it is. Now, another thing, urea is the natural end product of protein metabolism. So I don't know if you've ever changed a wet diaper before. What does it smell like? It could smell pretty strongly of ammonia. Why do you think that is? Because we know that ammonia is NH3. Well, look what's in urea, which is the main component of your Tinkle-Winkle. All right. You see this NH2 group, so it also has a pretty potent smell, all right? And it is a natural end product. That's how your body gets rid of this end product of protein metabolism, all right? And it says the average adult gets rid of approximately 30 grams, so it's about, 30 milliliters of urea in urine daily, okay? And urea is also produced commercially from carbon dioxide and nitrogen, and ammonia to make fertilizer. Okay, very important component for the agriculture industry. Okay, so it is a very important molecule historically and, in today's world too. All right, let's go on. All right, so let's talk about properties of amides. Okay, they're highly polar. Well, why do you think that is? What elements are found in amides? You find you have oxygens and nitrogens. What do you know about those? Those are 2 of the 4 highly electronegative elements: fluorine, oxygen, nitrogen, and chlorine. So there's 2 of the 4 very electronegative elements forming highly polar molecules. And what else? They are both have forms hydrogen bonds, all right? Not because of the oxygen. There's no hydrogen. Look down here. There's no hydrogen on the oxygen, so this is not where hydrogen bonding occurs. It is right here where the nitrogen has the hydrogen attached to it. All right, so because of this, amides have what? High boiling points, all right? High melting points, high viscosity, higher density. We've talked about all those things, okay, because of the hydrogen bonding. But if amides are secondary or tertiary, actually the boiling and melting points are lowered. Let me just show you again. This right here has hydrogen bonding. This here does not. You do not have a hydrogen directly attached to the nitrogen. All you have here is dipole-dipole only because of this oxygen. When you have this nitrogen, surrounded by all these carbons, you are really reducing the polarity of the nitrogen. It's slightly polar. It's slightly not symmetrical. Remember, you have a lone pair here, 2 electrons up here, making it bent. But you have these carbon groups. You are really not making that nitrogen bond as polar now as this oxygen that has nothing else on it besides the one carbon. So when you have especially a tertiary amide, you are really lowering its boiling point and its melting point. So why is that? I have less hydrogen bonding, or you have no hydrogen bonding if you have a tertiary. Okay, so for example, I gave you some of these. Whoops, there they are. And so here's your methanamide, which has a boiling point of 210 degrees Celsius. All right, what happens if I replace these two hydrogens with carbon groups? Now you have a lower boiling point. You have NN, that stands for you have two groups on the nitrogen, dimethylmethanamide. Now, it could be a whole lot worse. It could be a whole lot lower boiling point, but you've increased the molar mass of this instruction. So your London dispersion forces are a little bit greater. Not enough to make it a higher boiling point. You'll see the same thing. Here's your ethanamide. Why is ethanamide slightly higher than methanamide? Because it has a slightly higher molar mass, so it has slightly stronger London dispersion forces. All right, what about this one? It's your NN dimethyl. Again, what's on this N here? All right, I have two methyl groups. So you have, if it's a tertiary, you need to have an N and an N. We'll talk more about this with amines, so by the way, and then an ethanamide. And notice its boiling point is a little bit higher than the dimethyl methanamide. All right, but not as high as ethanamide, is it? Okay, so it has higher London dispersions because of the greater molar mass, but not enough to overcome the fact that it lost its hydrogen bonding. Okay, so reactions, let's scroll down here. All right, amides are made by heating carboxylic acids or esters with ammonia. All right, and so folks, this reaction is actually quite a bit more complicated than what it would look. The mechanism is a little bit more complicated than what you might assume. But anyway, it still goes. If you can make water, you will, all right, but it's not your first step, let's put it that way. So one of these hydrogens are given to the OH, if you will. Here's your water, and then the nitrogen with the two hydrogens left will make your amide. Okay, and that is all I'm going to do today. We will see you next time with the last video. All right, talk to you later. Bye-bye.